All right, welcome. Today, we're going to put on our detective hats and dive into a bit of a geometric mystery. We're going to be looking for clues, uncovering some pretty cool secrets, and cracking the case of how completely different shapes can actually take up the exact same amount of space. Let's get started with our first piece of evidence.
So let's start with a puzzle. Take a look at these two shapes. We've got a long, kind of skinny 9 by 4 centimeter rectangle and a perfect 6 by 6 centimeter square. I mean, at first glance, they look totally different, right? But here's the question. Could they secretly be hiding the exact same amount of area? Let's dig in and find out.
So here's our game plan for cracking this thing. First, we got to get our definitions straight. What's area? What's congruence? Then, we'll uncover a super important rule that's going to guide our whole investigation. From there, we'll expose the secrets of parallelograms and triangles, and you know I'm not going to leave you hanging. At the end, I'll give you a cheat sheet with all the key stuff. Okay, first things first. Every good detective knows you have to start with the basic facts. So let's get crystal clear on what we even mean when we're talking about area.
You know, when you draw any closed shape on a piece of paper, a square, a circle, whatever, that space inside the lines, that's what we call a planar region. And the area is really just a number we use to say how much space is in there. That's it. Simple as that. Now, this slide right here is a huge clue in our investigation. So on the left, you've got congruent figures. Think of them like identical twins. They have the exact same shape and the exact same size. So of course, their areas have to be equal. But look at the right. This is the kicker. Just because two shapes have the same area, it does not mean they have to be identical. They can look completely different.
And boom! Here is the solution to our first puzzle. That 9 by 4 rectangle, the area is 36. And the 6 by 6 square, well, 6 times 6 is also 36. So there you have it. They have the exact same area, even though they look nothing alike. This is a massive piece of the puzzle. Equal area does not mean identical shape.
Okay, so we know that different-looking shapes can have the same area. But how can we tell just by looking? Is there a shortcut? Well, yes, there is. There's a secret rule that's going to help us out, and I like to call it the common ground rule.
The first part of this rule is super simple. The shapes have to share a side. They need to be built on the same foundation. See here? Both of these shapes are sitting on that same bottom line, DC. That's what we call the common base.
Now, for part 2 of the rule, the shapes have to have the same height, basically. And what that means is that all their top corners have to line up perfectly on a single straight line that's parallel to the base. It's like they're perfectly sandwiched between two parallel lines.
This rule sounds pretty easy, right? Same base, same parallels. But hold on, because there's a really common trap that a ton of people fall into. Let's make sure you're not one of them.
And here's the mistake in action. Check this out. Both shapes are on the same base. Great, but look up top. Their corners are all over the place. They're not on the same parallel line. Since they're not neatly sandwiched, our special common ground rule doesn't apply here. This is a huge thing to watch out for.
All right, now that we understand the common ground rule, we are ready for a major breakthrough in our case. This is where the investigation gets really good.
And here it is. This is a total game changer. It's a theorem, a proven fact, that says if you have parallelograms that follow our common ground rule, you know, for a fact, that they have the same area. You don't even have to calculate it. So take a look at these two parallelograms. They look pretty different, don't they? One's kind of slanted, the other's more stretched out. But look closely. They both have the same base, DC, and yep, their top corners are on the same parallel line. They fit our rule perfectly.
So why on earth does this work? It's actually really cool. It's like a little magic trick. You see those two little triangles on the ends? ADE on the left and BCF on the right? They are identical. They're congruent. So, just imagine you could slice off that triangle on the left and just slide it over to the right. What happens? You've literally just turned the first parallelogram into the second one. Since all you did was move a piece, the total area had to stay exactly the same.
So, we've totally cracked the case for parallelograms. But what about triangles? How do they fit into this whole picture? Okay, here's our next piece of evidence. We've got a triangle and a parallelogram. And would you look at that? They are following our common ground rule. Same base, BC, and they are perfectly sandwiched between those same parallel lines. And whenever this happens, whenever you have this setup, there's a simple and really powerful connection between them.
The area of the triangle is always exactly half the area of the parallelogram. Not sometimes, not most of the time, every single time.
And this leads us to another huge breakthrough. So think about this logically. If one triangle is half of a parallelogram, and another triangle is half of a different parallelogram, and we already proved those two parallelograms have the same area, what does that tell us? It means the two triangles must have the same area as well. Pretty neat, huh?
We did it! We've cracked the case! We've figured out the secrets of parallelograms and triangles. So now let's pull all these clues together into a super handy cheat sheet for you.
This is your ultimate cheat sheet. Seriously, go ahead and take a screenshot. It's got everything you need to know. The key difference between area and congruence, our big common ground rule, the two huge theorems we just proved, and even a little bonus tip about medians. It's all right here for you.
All right, let's put our new detective skills to the test with one last case. Remember that farmer, Budia, who wanted to divide her triangular field into 3 equal parts for her kids? All she did was split one side into 3 equal pieces and then drew lines to the opposite corner. Did that actually work? Was she right?
And the answer is yes. It worked perfectly. She absolutely nailed the geometry. By creating 3 new triangles that all have equal bases, and since they all share the same top corner, they all have the same height. And if they have the same base and same height, they have to have the same area. It's a classic example of these geometric principles in the real world. Case closed.